Hey guys, this is Mr. Varela, and the following is a lecture video for Chapter 6.1, Observing Chemical Changes, and this is for my 8th grade science students for 4th and 5th period. If you are in 7th grade, you're at the wrong video. You need Chapters 10.1, which is also already on my YouTube site, so please close this one and click on the other one. Okay, so for 8th graders, before we begin, you will need your Chapter 6 classwork packet. This was passed out on Friday. For those of you that were absent on Friday, I mailed out the classwork and the homework packets, and I put it in the mail on Saturday. You should get it by Tuesday, no later than Wednesday, the 18th. Okay, if you don't get it, or if you lose this packet, you could always go to my website and download and print it. Okay, if you're unable to download or print it, I do have extra copies of my own. Email me at my school email, and I'll figure out how to get you a copy of it. Okay, so before we begin on the notes, be aware that we still have key terms. As always, you need to do the picture in the box, and you have to use at least 4 colors, and then the definitions have to be looked up in the back of the book. You do need your science book to do this, and also for your homework packet, you will need your science book to do the reading and note-taking worksheets. If you do not have a science book, unfortunately, there is no book available online. You were told to talk to Miss Mary and get a copy of the book from the library if you didn't have one, or if you lost your previous copy. If you don't have your book, you're going to have to skip this section and do it later when we come back, and I'll just give you half credit because it'll be late. But you do not need your book to do this part, which is the notes right here. Chapter 6.1, Observing Chemical Changes. Here are the notes. Now, the notes, I'll put it up here on the screen. This is available on my website. If you want, you could always pause the video and copy the notes, but it's available on my website. I'm going to go fast because this is only, the lecture is only for the Cornell Notes that goes here on the side and then the summary. Remember, you need to put 3 things that you learned or 3 questions that you have, or a combination of both. And the summary has to be a 1 to 2 sentence summary of summarizing everything. Please do not be vague. Some of you have been writing vague things like, oh, for summary, I learned about chemistry. That's too vague. We're going to be learning about like physical and chemical properties, so give me a 1 or 2 sentence summary about everything that we learned. Okay, so let's begin. All right, the EQ is how can you tell when a chemical reaction occurs? Now, what we're going to learn is every time that a chemical changes, it's not always a chemical reaction. For example, if you have ice, which is basically solid water, and it melts into liquid water, that is not a chemical reaction because of the fact that it's still water. It went from being solid ice to a liquid, which is what we drink. But then that liquid could be frozen back into an ice cube, and it could go back and forth. The chemical reaction is more permanent. For example, if you're tired of taking Cornell Notes and you just decide to take this packet and burn it up in the fireplace, that is a permanent reaction because that paper now turns to ash, and the ash cannot go back to being this paper. When that change is permanent, we call that a chemical change. So let's look at the difference between a physical property and a chemical property. For a physical property, it's something that doesn't require it to change. For example, the color. The color of an item doesn't change. If you have, for example, copper and you melt it. If you melt it into liquid, it's still a copper color, which is like reddish brown. If it turns hard back into metal, it's still a copper color. The texture of an item, you can make something smooth or you can make it rough. For example, you can make an ice cube that could be very, very smooth, but you could also maybe make an ice cube that has sharp edges. So an item could be sharp or it could be smooth. It's still ice or whatever it is. Is it soft or hard? That is a physical property of an item. Some items are soft, like even some metals. For example, pure gold is actually pretty soft. You could cut it with a knife. Or some metals are inherently hard. Does it conduct electricity? Does it conduct heat? That's thermal conductivity. When does it melt? When does it boil? These things do not actually change your element. So if ice, for example, boils at 100 degrees Celsius, it's always going to boil at 100 degrees Celsius. It's not going to change the fact that it's water after it boils. It'll boil into steam, which is just a gaseous version of water, but it's still water. Now, what about a chemical property? Chemical properties describe something where it will change into something else. For example, flammability. We talked about paper or wood. If you burn it, it catches on fire, turns to ash, and you can never make it go back to being paper or wood. Does it react with another substance? For example, if the acid reacts with the base, it will combine, it will become something else, and you may not be able to change it back. Will it rust or will it tarnish? When a metal is exposed, well, most metals are exposed to water, for example, iron, it will rust. And once it turns into rust, that's permanent. Now, and tarnish, by the way, if you don't know what tarnish is, if you've ever seen a brand new penny versus an old penny, a brand new penny has like a reddish brown color to it versus an old penny is kind of green. Well, that green is a patina. And that's basically what happens with copper when it's exposed to water. Now, you could always clean a penny, but what you're really doing is you're just rubbing off that patina off the penny. It's a chemical reaction, and that copper actually permanently changed. Same thing with rust. If you see rusted metal, you could always sand it off, but really you're just sanding off what used to be metal and turned to rust. I mean, eventually, whatever rust you sanded off of the metal, that metal will rust again. And if you keep sanding and sanding, you're actually removing layers and layers of metal. The metal is permanently turning, it's oxidizing into something else. You can never turn rust back into metal. Same way you can't turn ashes back into paper or wood once you burn it. Okay, next slide, continued. We're still talking about physical and chemical changes. A physical change will could alter the way it looks, but it doesn't change the substance into something else. For example, this pencil. If I break the pencil, I change the way it looks. And, it's still a pencil. Even though it's a broken piece of pencil, you might be thinking, well, if you broke it, it's never going to be the same again. If you glue it, you could tell you broke it. That's true, but the thing is that even these parts are still pencil. I could still sharpen this pencil, and now I have like two pencils. Now they're smaller. The pencil's job is to write stuff down, and even though I broke the pencil, I could still do that. That is a physical change. I may have broken the pencil, however, it's still a pencil. Now imagine if I burned the pencil. If I burn the pencil, I can never use it to write. It's been a permanent change. So for a chemical change, it's a change in matter that results in something new being formed, oftentimes with different physical and chemical properties. For instance, this marshmallow, if anyone's ever done s'mores, you realize that marshmallows could catch on fire. And when they do catch on fire, you actually make something new. If you burn it all away, it turns into ash. Now, I'm not talking about a marshmallow that's slightly burned. I'm talking about one that you burned everything. There's no more marshmallow in there. It's just ashes. It tastes the same. It looks the same. It feels it doesn't taste the same. My bad. It tastes different. It looks different. It smells different. It has a different texture. Marshmallows are squishy, and this burnt ash is brittle. So, my bad. It changes completely. You can never go back. It doesn't serve its purpose anymore. Same thing like the pencil. If you burn the pencil, it's no longer a pencil. Okay. Now, what if I cut the marshmallow in half into like two mini marshmallows? Well, that would be then a physical change, because I just turned a bigger marshmallow, cut it in half, into two smaller ones. Kind of like if I take the pencil, cut it in half. It's still a pencil, albeit smaller. So chemical change requires the item to be chemically changed to something else. Now, another thing I want to bring up where sometimes it has different chemical properties. I mentioned obviously that this marshmallow is flammable, but have you noticed that once you burn something, it no longer catches on fire? For instance, if you burn this pencil and it turns into ash, the ashes are no longer flammable. They won't catch on fire. Okay, so if you burn this marshmallow to a crisp and you put this under fire, this wood is no longer flammable. So now it has a different chemical property because this was flammable and now this one's not. Now, it's not always irreversible for chemical changes. There are some exceptions, but for the most part, chemical changes are permanent. And for the most part, physical changes are usually reversible. Like an ice cube can melt to water, water could freeze back into ice, and this pencil could be broken, but we could glue it together, it's still a pencil, okay? Now, and I mentioned right here again, with water. Here, for example, ice can turn into water, water could go back to ice. Basically, H2O solid can turn into H2O liquid, and H2O liquid could go back. Notice the arrows are going back and forth, okay? Now, Here, notice the arrows only go one way. Once you have a marshmallow catches on fire, it's now something else. It's not a marshmallow. Here, this is one-way reaction. We have two H2s. H is hydrogen. That's an H and that's an H. That's H2, and now we have another one. So we learned this earlier, but because of the school closure, we never really got to, we talked about superscript and subscripts, but we never really got to coefficient. H2 means that's two hydrogen molecules together, and 2 means that we have two of them. And here we have O2, oxygen with oxygen. Now, when we put it together, what we end up getting is two of these H's hook up with one of the O's, and the other two H's hook up with the other O, and we get 2H2O. This is liquid water. H2O, two H's and an O, and we have two of them. So this is a one-way reaction. Now, I did mention it's usually irreversible. We can actually turn liquid water back into hydrogen and oxygen. However, it wastes a lot of energy. Why is that significant? H2 is very flammable. Future cars, I don't know if you heard of like fuel cells. The future of basically of cars is to replace gasoline with hydrogen power, where you could basically turn water. We could find out an economical way to turn water and break it down into H2 and O2. This is the oxygen we breathe. So instead of cars polluting nasty chemicals, the only thing it would, quote, pollute, unquote, would be pure oxygen. And the H2 would be used to burn in the combustion chamber. So we have, if you think about it, it's water. Earth is 75% water, so we have unlimited fuel. But this is very difficult to go H2O to H2 and O2. That's why normally in nature we say it's usually irreversible. We need some handy, smart scientists to figure out how to make this equation go backwards. But in nature, for the most part, it goes one way. Now, a physical property may be altered, but the chemical composition stays the same. So, for instance, it's still water. We went from solid to liquid, but it's still water, it's still H2O. But here, notice that bonds are broken. Notice that the two red dots, the hydrogen, there's a line that's a bond. And between the two green dots, that's a bond. Notice that the bonds had to be broken to squeeze one of these green dots in the middle. We had to break this bond and break this bond. So whenever bonds are broken, that is going to be a chemical change. But for physical change, the bonds are retained. You don't break bonds. Going from ice to water, liquid water, and liquid water back to ice does not require any of these black lines, any of the bonds to be broken. It's just, again, it's a physical change, not a chemical change.